Okay, see now the torsion examples of for the procedure. Now see that technically most probably these questions torsion in the examples where we have to design a beam or the flexural member for these questions are going to ask for the 10 marks. Okay, now the total steps are involved in this 1 to 9 steps are going to be there. In the first step you are going to write the given data, step 1. Now in that given data most probably in the question they will give given data, firstly the width of beam or the flexural member, and that will be denoted by B. Okay, then the depth of beam, and that is D. Okay, now the shear force, and that will be denoted by VU. Okay, now the next one is the bending moment. It will be denoted by MU, and the torsion moment, it will be denoted by TU. Okay, now in the question there will be the value of M, means the mixed design of the concrete, means the grade of concrete. Okay, if for example, okay, that is M20. Okay, now see, it means that they have two values, okay, which are being given. The firstly that will be FCK, characteristic strength, and if it is M20 then we will have the 20 Newton per mm square, and the another will be sigma CBC. Okay, and that value will be 7 Newton per mm square. Now see, for M20 that is FCK, it is 20 Newton per mm square, but how we calculated the value of sigma CBC? Okay, for that term we have to see the IS 456 2000 and look on the page number 81. Okay, there will be a table number 21. In that table number 21 we will get the value of sigma CBC. Okay, I will show you. Okay, now see the permissible stress in concrete. Now M20, see the bending, and here it is the value, that is 7.07 Newton per mm square. Okay, up to here it is clear. Now the next one term, that is the grade of steel. Okay, grade of steel. Now if for an example the grade of steel is Fe415, okay, here also we have the two values of it. The first value is yield stress Fy is equal to 415 Newton per mm square. Okay, and what will be this value? That is sigma St. Okay, the permissible stress in steel. Okay, that is 230 Newton per mm square. Now you can ask me that, sir, if the Fy value is 415, it is very easy to find out the value, but sigma St, how we know that that is 230 Newton per mm square? Now for this reason also we have to go on the IS 456 2000, see the page number 82 of table number 22. Okay, see in this, that is 230. Okay, see the HYSD bar Okay, now the grade is Fe415, and for Fe415 that is 230. Okay, now the next thing means the step number 2. Okay, step second. Now for the step number second, it will be design constant. See, this step is only applicable if the dimension of depth is not given in the example. Means in this step we are going to find the value of d. So for that, see, the formula is not given, so I will write this with the red pen. That is mu is equal to 1 by 2 JCB KCD square. Okay, now what do I do when the example by solving the value of d or concluding the value of d, and if it is not able, that the IS code is not given, so in that particular time I most probably do these things JCB. Okay, means this term is noted down JCB KCD d square. Okay, now for the finding the value of d, how we will do? See, the d is in square, so is equal in root. Okay, that is mu. Okay, the whole term is multiplication to the d, so that is 0.5 into JCB into KC. Okay, now see the mu which is given, that is bending moment. Okay, right. Now the value of j is 1 minus k by 3. Okay, now what is k? The k is equal to 1 upon 1 plus 0.0107 of sigma st. Okay, permissible stress in steel. Now see, the value of c we don't know. The c means sigma cbc, means the permissible stress in concrete. See, for example, that is M20 grade. Here we will get the value of 7 Newton per mm square. So by putting this all value, we will get the value of d, and the value of d will be noted by unit mm. Okay, the second step is clear. Now for the third step, step 3. Now here we will find the equivalent shear, means the value of VE. Okay, now for value of VE we don't know the formula, so again open the IS 456 2000 page number 75. Okay, in that clause number 41.3.1. now the formula is VE is equal to VU plus 1.6 TU by V. Okay, from this we will get the value of equivalent shear. Okay, now the step number 4. Step 4. Okay, in this we will find the nominal shear stress. Okay, that is tau VE. Okay, it is in tau VE. Now that is, we have to remove again IS code IS 456 2000, in which page number 72 and clause number 40 0.1. Okay, see, the tau VE is equal to VE means the equivalent shear divided by BD. Okay, here we will get the value of nominal shear stress. Okay, we are till the step number 4, means the half of the example it is done. Now the next step. Okay, for the next step we will find the, see, the step number 5. Okay, step number 5, design shear strength of concrete. Okay, the design shear strength of concrete. For this, see, we will assume percentage, and that will 0.25. In general, mostly that is 0.25. Now for M20, okay, see, again open the IS 456 2000, in that page number 73, table number 90. Okay, now here you will get the value of tau c is equal to 0.36 Newton per mm square. Okay, now next to it, it will have the next table, that is tau c max. For the tau c max, it is 2.8 Newton per mm square. Okay, of IS 456 2000, page number, same page 73, and the table number 20. Okay, see, I will show you now. That is page number 73. See, page number 73, in that table number 19. Okay, that percentage was 0.25, this one. Okay, and our grade of concrete was M20, so that is 0.36. Okay, now for the tau c max, table number 20. Okay, as per the grade, that was M20, and the value of tau c max is 2.8 Newton per mm square. Okay, up to here it is clear. Now we have to just check that whether the value of the shear stress is correct or not. So the condition is tau c, shear capacity of concrete, should be less than tau v, nominal shear stress, less than tau c max. Okay, if it satisfies this condition, then step number 6, and if not, leave the example up to here only. Step 6, here equivalent bending moment means ME1. Okay, it is denoted by ME1. Now for this, again open IS code 456 2000, in that page number 75 of clause number 41.4.1. see, the value of ME1 is equal to MU, bending moment, plus torsion moment, MT. Now we know the value of TU, but MT we don't know. Now for that, TU 1 plus overall depth divided by B whole divided by 1.7. Okay, now that if, see, the value of MU1, equivalent bending moment, there is also a condition, if MU, okay, is less than MT, okay, then in that case we have to find ME2. Okay, and that will be mt minus mu. Okay, now nextly we will find the area of steel. I will just bracket it so that you will able to understand more. Okay, this is for me1 and this is for me2. Now step number 7. In this we will find the area of steel and it is denoted by AST. Okay, for this the formula is not given in IS code, so you have to memorize it, and the formula is AST is equal to 0.5 FCK 0.5 FCK divided by Fy in bracket 1 minus in root 1 minus 4.6 mu divided by FCK BD square whole bracket close into B into D. Okay, this is very important formula, you have to memorize it. Now the mu, while finding the AST1 and AST2, only you have to change the equivalent bending moment, that is ME1 and ME2. Okay, from that you will get the value of AST1 and AST2. Okay, so after that you will know the area of steel. And here the step number 8. In this case we have to check for minimum area of steel. Okay, now that is denoted by AST minimum. Okay, we have to find it, right? Now for that open your IS code 456 2000, in that page number 47 clause number 26.5.1. okay, in this the IS code it is given like this: AST minimum divided by B into D is equal to 0.85 divided by F1. So we have to find AST minimum, that is AST minimum, it is at the bottom side, so numerator denominator, so it will come at this side 0.85 BD divided by F1. By this you will get the value of AST minimum, and nextly you have to find that the number of bars. Okay, that is total AST divided by bar. In this condition assume 12 mm diameter bar. Okay, then you will get the number of bars. Okay, now you have to check that AST minimum should always be less than total AST. Okay, then simply you have to draw the diagram, and that is section of your flexural member. Okay, now for example we have 3 numbers of bar at the tension side. Okay, now this will be our D dash, means the cover. The B is the width of the section, capital D is the overall depth. Now this is x1 distance, this is y1 distance, and plus we have to find this distance, and that is D1 and B1. Okay, now how we will find that? For this the B1 is equal to width minus 25 minus 25, and d1 is equal to overall depth minus 35 minus 25. Okay, and plus x1 is equal to b1 plus 2 in bracket half of bar diameter plus 2 into half of into 8. Okay, here you will get the x1 value, and y1 is equal to d1 plus 2 into half of 1.2 by 12 plus 2 into 1.2 by 8. Okay, now up to here it is clear. Then our last step means the step number 9, and here we will find the transverse reinforcement. Now how we will find it? Again open the IS code 456 2000, in that page number 75, clause number 41.4.3. see, firstly we have to know that the ASV, area of steel in vertical. Now assume 8 mm diameter vertical two-legged stirrups. Okay, right. Now means the ASV, number of bars into pi by 4 into d square, and that will be 100.58. that is value of ASV. Now we get the value of ASV, that is in the mm square. Now the lastly, that is the spacing. Okay, it is denoted by SV. There are three things. Now for the spacing, see IS 456 2000, page number 75, clause number 41.4.3. okay, in that you will get ASV is equal to TU SV divided by P1 D1 0.87 Fy. Okay, plus VU SV divided by 2.5 D1 0.87 Fy. Okay, now see, SV divided by 0.87 Fy, SV divided by 0.87 Fy means that we will take it in a common. Okay, then we will get ASV is equal to SV divided by 0.87 Fy into TU divided by B1 D1 plus VU divided by 2.5 D1. Okay, now take SV at this side, that is SV is equal to ASV into 0.87 Fy divided by TU by B1 D1 plus VU by 0.5 times of D1. Okay, by this you will get the value of SV first, then second ASV tau VE minus tau C in bracket B into SV whole divided by 0.87 Fy. Now for SV, that will be ASV is equal to ASV into 0.87 Fy whole divided by tau VE minus tau C, okay, into B. Okay, now and the last is condition, that is SV should not be greater than 300 mm, and this is okay, and this is the final. If both the values are greater than 300, then they take the value of SV, means spacing is equal to 300 mm, and here your example is completed. Thank you.